Good morning, all of you. Welcome to Jayendra Rank Zone. Now we are going to do H block elements continuation. In the first lecture, we have done general properties, general physical and chemical properties of H block elements. Now, this is the second lecture we are going to discuss now. In this lecture, we are going to discuss about some more properties of H block elements. So, please listen carefully. Yes, now we have started second lecture, lecture number 2. In the first lecture, we have done general physical properties and chemical properties of H block elements. Now we are going to do some more properties of H block elements with some important compounds, and we are discussing only group 1 now. Next we'll discuss group 2 also. Now next we have compounds of alkali metals. So what are the compounds they will form? Alkali metal generally. Let us start now. General characteristics of oxides in hydroxides. Alkali metal combines with oxygen directly in air to form respective oxides. Very, very important. Lithium forms mainly monoxide, that is lithium monoxide. Sodium forms peroxide, and other alkali metal forms superoxide. This point is very important. So superoxide is paramagnetic in nature. So potassium will form superoxide. That is the formula is KO2, and the oxygen state of oxygen is minus half in superoxides. Rubidium also forms superoxide, and cesium also forms superoxide. In superoxide, the oxidation state of oxygen is minus half. In superoxide, the oxygen state of oxygen is what? Minus half. The stability of peroxide and superoxide increases with the increasing size of alkali metal ion. So what do you understand by this? The stability of peroxide and superoxide increases with the increasing size of alkali metal ion. So cesium superoxide is more stable than rubidium superoxide than potassium superoxide, because the size of cesium is bigger than rubidium and potassium because due to its highest atomic number. These oxides dissolve in water to form respective hydroxides. So this superoxide, cesium superoxide or rubidium superoxide, dissolve in water and forms cesium hydroxide, OH taken twice. So these are the products now. This is about the nature of oxides and hydroxides. Alkali metal combines with oxygen in air to form respective oxides. Lithium mainly forms lithium oxide, Li2O. Sodium forms sodium oxide along with sodium peroxide. Potassium will form potassium oxide. So not only this, sodium forms peroxide means it doesn't mean that sodium will not form sodium monoxide. Sodium will form monoxide as well as peroxide. What is the formula of sodium peroxide? Na2O2. So in peroxide, the oxygen state of oxygen is -1. The oxidation state of oxygen is -1. Anyway, however, alkali metals will have always +1 oxygen state only. So this is +1, this is +1, this is +1. And in superoxide, the oxygen state of oxygen. So sodium will form sodium monoxide as well as sodium peroxide. Whereas potassium will form potassium monoxide, potassium monoxide, potassium peroxide, as well as potassium superoxide. So these are the three oxides will be formed by potassium. So potassium can form potassium monoxide, potassium peroxide, and potassium superoxide. What is the formula of potassium peroxide? K2O2. I'll repeat again and write. The formula of potassium peroxide is K2O2. Similarly, rubidium also will form rubidium oxide, rubidium peroxide, and rubidium superoxide. And cesium also will form superoxide, cesium superoxide, cesium peroxide, and cesium oxide. So in all these things, and as we go down the group, with the increasing size of alkali metal ion, the stability of peroxides as well as superoxides increases with the increasing size of alkali metal ion. But it's what you understand. Cesium superoxide is stable when compared to rubidium superoxide and potassium superoxide. So these are the various types of oxides the alkali metals will form. So in the oxide, they'll ask us what is the oxygen state of oxygen also. So please remember that. Normal oxides form hydroxides, very, very important here. So normal oxides are lithium oxide, potassium oxide, or sodium oxide, that is lithium oxide, M2O. So normal oxide forms hydroxide, peroxide form hydroxide and hydrogen peroxide, and superoxide forms hydroxide, hydrogen peroxide, and oxygen. Very, very important. These reactions definitely they'll ask in the examination. So when you dissolve normal oxide, here M is called M. Here M is equal to, it can be lithium, sodium, potassium, rubidium, cesium. So in this case, because all will form normal oxides. So when you dissolve normal oxide in water, definitely there is sodium monoxide, lithium monoxide, potassium monoxide, rubidium monoxide, cesium monoxide. All these normal oxide when dissolved in water forms the respective hydroxide, that is lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, as well as cesium hydroxide. In this case, when you take here M is equal to, lithium will not form peroxide. So only sodium, potassium, rubidium, and cesium. Please note down this. So when peroxide is dissolved, what is the oxidation state of oxygen in peroxide? -1. Normal oxide is -2. And superoxide it is -1/2. Very, very important point. Please note it down. So in case of peroxide, when peroxides are dissolved in water, it forms hydroxide along with hydrogen peroxide. So metal hydroxide along with hydrogen peroxide. So for example, when sodium peroxide dissolves in water, it forms sodium hydroxide along with hydrogen peroxide as byproduct. Here, this is very important. Next, similarly, when superoxides are dissolved in water, they form their respective hydroxides, that is potassium hydroxide, sodium hydroxide, rubidium hydroxide. Anyway, in this case, M is equal to sodium will not come. So in this case, only M is equal to potassium, rubidium, and cesium. Remaining all will not form. Means this will not form by sodium and lithium. Sodium superoxide will not form, as well as potassium. Sorry, this lithium also will not form superoxide. So this is the trend of reaction of oxides and hydroxides of alkali metals. So you can see here peroxides, when dissolved in water, forms hydroxides along with hydrogen peroxide. So when sodium peroxide dissolves in water, it forms sodium hydroxide and hydrogen peroxide. Potassium peroxide dissolves in water, it forms potassium hydroxide and hydrogen peroxide. Rubidium peroxide dissolves in water and forms rubidium hydroxide and hydrogen peroxide. Similarly, cesium peroxide dissolves in water, will form cesium hydroxide along with hydrogen peroxide. So in place of M, you can keep sodium, potassium, rubidium, or cesium. And in the first case, in case of M, you can keep all the alkali metals except francium. Second case, except lithium and francium, all other alkali metals. Third case, only potassium, rubidium, and cesium only will form superoxides. No other alkali metal like that is. So lithium and sodium cannot form superoxides. Lithium and sodium cannot form superoxides. So when these superoxides are dissolved in water, they form their respective hydroxides along with hydrogen peroxide, and oxygen is the byproduct. What is the byproduct again? Oxygen. So these three reactions are very, very important. Definitely they are going to ask in the examination. Please note it down. Next continuation. The oxides and peroxides are colorless while superoxides are colored. Why superoxides are colored? Because they are paramagnetic in nature. Very, very important point. All the superoxides are colored because they are paramagnetic in nature. Paramagnetic in nature means they contains unpaired electrons. They contain unpaired electrons. So that's why even they'll ask them how to calculate the magnetic moment of these superoxides also. So superoxides are paramagnetic in color. The oxides and peroxides are colorless, while superoxides are yellow or orange in color. So potassium superoxide yellow color or orange color, and rubidium superoxide, cesium superoxide also same. The hydroxides of alkali metals are white crystalline solids. So what is the hydroxides of alkali metals? Like potassium hydroxide, sodium hydroxide, rubidium hydroxide, cesium hydroxide, lithium hydroxide. They are all white crystalline solids and highly soluble in water. However, lithium hydroxide is sparingly soluble in water due to crystallization, due to its hydration enthalpy. Due to its high hydration enthalpy, it is sparingly soluble in water, and moreover, it is covalent. Due to its high hydration enthalpy and covalent nature, covalent character, lithium hydroxide is sparingly soluble because all covalent compounds are not soluble in water. Due to covalent character, lithium hydroxide is sparingly soluble in water. This point is also very important. So among all the alkali metal hydroxides, lithium hydroxide is sparingly soluble. Remaining all hydroxide, that is sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide, are strongly soluble in water. Hence, they are also called as soluble. So these hydroxides are strongly basic in nature. That's why they are also called as alkalis. Why they are called as alkali? Because soluble bases. Alkali meaning is what? Soluble base. Soluble base is the meaning of alkali. So that's why they form alkalis. So the hydroxides of alkali metals are white crystalline solids and highly soluble in water. However, lithium hydroxide is sparingly soluble in water due to its high hydrogen enthalpy and covalent character. These hydroxides are strongly basic in nature. So please listen carefully. All these points are very important. Very, very important point in this is superoxides are paramagnetic in nature as they contain unpaired electrons. So they'll ask us how many unpaired electrons. Usually they have one or two unpaired electrons. In case of potassium superoxide, it has two unpaired electrons. In case of rubidium superoxide, so any superoxide, it have only one unpaired electron. So due to which what happens, you can find even magnetic moment also. So magnetic moment is calculated by using the formula mu is equal to root of n into n plus 2. So that we can find magnetic moment of Bohr magnet, and this is the unit. So we can find the magnetic moment of potassium superoxide, sodium, rubidium superoxide, and cesium superoxide. So please calculate these three magnetic moments because that is important for our entrance examination. So calculate magnetic moment of potassium superoxide, rubidium superoxide, and cesium superoxide by finding the number of unpaired electrons. Anyway, we are going to discuss that also. So please do this. Next continuation. So whatever I'm writing here and what are the slides we are getting displayed while you are watching this class, definitely each and every slide you make a note in your classwork, then only you can understand it better way. Otherwise, you'll forget everything. So my sincere request is that all the students should write the given slides and whatever I'm explaining part in the red pen or any other pen, you have to write in your classwork, then only you can understand the concept better. If you understand the concept better, easily you can solve the questions in the entrance exam. So please do that instantly. Next continuation. Alkali metals forms halides of type MX. Which type? MX, like NaCl, NaF, NaBr, NaI. That is sodium iodide. So we'll call it as alkali metal iodide. Alkali metal iodide means sodium fluoride, sodium chloride, sodium bromide, sodium iodide. Potassium fluoride, potassium chloride, potassium bromide, potassium iodide. So all alkali metals will form halides of type MX. The halides of alkali metals are crystalline solids with high melting points because they are ionic in nature. All the alkali metal halides are ionic in nature. So as they are ionic in nature, they are having high melting points and boiling points. So these halides are prepared by the reaction of oxides, hydroxides with aqueous hydrohalic acid. Hydrohalic acid means any halogen. So oxide. So alkali metal oxide here M is equal to, your M can be alkali metals, all alkali metals, that is lithium, potassium, rubidium, cesium, francium, and sodium. Not francium, except francium. So M is equal to all alkali metals. So M2O on reaction to HCl, it forms MCl plus H2O. So the enthalpy of formation of halides of alkali metals is highly negative, indicating higher stability of halides. So all the halides are more stable because the enthalpy of formation of halides of alkali metals, the enthalpy of formation of halides of alkali metals is highly negative, means delta H is equal to negative enthalpy of formation, indicating higher stability of halides. Next continuation. The enthalpy of formation of fluorides becomes less negative from lithium to cesium. Means because fluorine is reaction of fluorine with alkali metals a little bit explosive. So that's why it is less negative from lithium to cesium. While the enthalpy of formation of chlorides, bromides, iodides become more negative from lithium to cesium. So lithium fluoride, sodium fluoride, potassium fluoride, and rubidium fluoride greater than halides, that is chlorine, bromine, and iodine. So for all this, it is more negative. For a given alkali metal, the enthalpy of formation decreases from fluoride to iodide. Fluoride is more, next chloride, next bromide, next sodium iodide. So enthalpy of formation decreases, very, very important this order. The enthalpy of formation decreases, that is sodium, heat of formation of sodium fluoride is greater than heat of formation of NaCl, heat of formation of NaBr greater than heat of formation of sodium iodide within the same alkali metal for a given alkali metal. Means like here we have taken the example of sodium. The same trend follows for all other alkali metals. The melting point and boiling point of alkali metal halides decreases from fluoride to iodide. All alkali, because alkali metal fluids are strongly ionic when compared to iodides. So that's why their melting points decreases from fluoride to iodide. All metallic. So what do you understand by this? Sodium fluoride is having more melting point than sodium chloride, than sodium bromide, than sodium iodide. This is the melting point order of same given metal. All alkyl metal halides are highly soluble in water except lithium halides. The low solubility of lithium fluid in water is due to high lattice energy, and the low solubility of cesium iodide is due to less heat of hydration of cesium and iodide ions. So these are the two exceptions. Lithium fluoride and cesium iodide are less soluble. In case of lithium fluoride, it is due to crystal lattice enthalpy. It is due to lattice enthalpy. And in case of cesium iodide, it is having low hydration enthalpy. Both are similar only, low hydration enthalpy. So due to these two things, low hydration enthalpy, H dot E. So due to these two things we have discussed, so that's why the low solubility of lithium fluoride in water is due to high lattice energy. This reasoning also they'll ask in the examination. So wherever you got reasoning and explanation, definitely should make a note of it. So the low solubility of lithium in fluid water is due to its high lattice energy, and the low solubility of cesium iodide is due to less heat of hydration of cesium and iodide ions. So please make a note of all these slides. Very, very important points. Any point they can ask in the entrance exam. Next, alkali metal forms salts with all oxy acids. General characteristics of salts of oxo acids of alkali metals. So, alkali metals form salts with all oxy acids. Oxy acids, it forms salts. These salts are generally soluble in water and have high thermal stability. So, the thermal stability of carbonates and bicarbonates increases down the group. Lithium carbonate, actually this should be Li2C3. Lithium carbonate is unstable towards heat and decomposed to give lithium oxide and carbon dioxide. Also, lithium bicarbonate is known only in solution state but not in solid state. Now let us see stepwise. Alkyl metal forms salts with all oxy acids. Means, for example, sodium metal combines with oxy acid like this, H2CO3, carbonic acid, or you can take HCl. You can take HCl, HCl. It forms sodium chloride along with hydrogen gas. So 2Na plus 2HCl gives us to NaCl, 2NaCl plus H2O. So alkyl metal forms salts with all oxy acids, sodium sulfate. So this is salt. Now coming to sodium combines sulfuric acid and forms sodium sulfate and hydrogen gas. So hydrogen gas is liberated in all these reactions. So this is sodium sulfate. Like this, alkali metal forms salts with all oxy acids. With sodium, with nitric acid forms sodium nitrate. With carbonic acid, it forms sodium carbonate and bicarbonate. So the thermal stability of carbonates and bicarbonates increases down the group. So means what? Lithium carbonate is more stable than sodium carbonate, is more stable than potassium carbonate, is more stable than rubidium carbonate, more stable than cesium carbonate. So down the group, the stability decreases. So lithium carbonate, similarly lithium bicarbonate. Bicarbonate, what is the formula? NiHCO3. Lithium bicarbonate is more stable than sodium bicarbonate and so on. So the thermal stability of carbonates and bicarbonates increases down the group. So it is increasing. So here we have to write increases means we have to keep less than significant. Increases down the group means we have to keep lithium bicarbonate is less stable than sodium bicarbonate. It is less stable than potassium bicarbonate, less stable than rubidium bicarbonate, less stable than cesium bicarbonate. Here also the same thing, less stable. So please make a note. That's what this will be very confusing. If you don't see the statement, it will be going. So the thermal stability of carbonates and bicarbonates increases down the groove. Next continuation. Now, these are the general physical and chemical properties of all the alkali metals. Now, in all the alkali metals, anomalous properties lithium. So lithium is quite exceptional when compared to all the alkali metals. That's what the topic is. Anomalous behavior of lithium. How lithium is different from all other alkali metals. Lithium shows anomalous behavior compared to rest of the alkali metals. This anomalous behavior is due to two factors. First factor is small size of lithium atom ion, high polarizing power. So because of these two factors, lithium is quite different from all other alkali metals, that is sodium, potassium, rubidium, and cesium. So why lithium shows anomalous behavior? Because of these two factors. What are the two factors? Small size of lithium, high polarizing power, that is higher charge by size ratio. The properties of lithium are comparable with that of magnesium. That's why they have diagonal relationship. Lithium is having diagonal relationship with magnesium. This is called diagonal relationship. Diagonal relationship. Why it is showing diagonal relationship? Because the properties of lithium and magnesium are almost similar. So they are comparable with that of magnesium. This similarity in properties of lithium and magnesium is known as diagonal relationship. So lithium will show diagonal relationship with magnesium. Lithium will show diagonal relationship with magnesium. So please make a note of it. Next continuation. Differences from other alkali metals. First point number one. All alkali metals are soft metals with low melting points and boiling points, whereas lithium is relatively harder with higher boiling point and melting point. This is the first difference. So among all the alkali metals, lithium is having higher melting point and boiling point, and moreover, it is harder when compared to sodium, potassium, rubidium, and cesium. Next, lithium is less reactive compared to remaining alkali metals. Lithium forms monoxide only, while other forms peroxides and superoxides. Lithium forms nitride, while other alkali metals do not form nitride. Means what? As I told you, lithium directly combines with nitrogen and forms Li3N. So it is 6 Li plus 2 N2. So it is nothing but 2 Li3N. So lithium not only combines with air it combines with oxygen as well as nitrogen. It forms lithium oxide. So lithium can combine with oxygen in the air and also nitrogen, whereas other alkali metals only form oxides and superoxides. It will not form nitrides directly. So lithium forms nitride while other alkali metals do not form nitride. This point is very important. Please note it down. All these anomalous properties of lithium points are very important. It shows how lithium is different from all other alkali metals. Next, very important, lithium chloride is deliquescent and form hydrated salt. Other alkali metals chlorides do not form hydrated salts. What is deliquescent means water soluble. Water soluble. So lithium chloride is deliquescent salt and form hydrated salts. So please note down these are the 3 points. Anomalous properties of lithium. Definitely they are going to ask anomalous properties of lithium in the examination, that is based on statement based question they'll ask. Fourth point, lithium bicarbonate is known only in solution state, while other alkali bimetal bicarbonates are known in solid state also. Lithium nitrate on heating gives lithium oxide along with nitrogen dioxide and oxygen, whereas other alkali metals nitrate give nitride. Very, very important. These two reactions are very important. So lithium nitrate on heating strongly forms lithium oxide, nitrogen dioxide. Nitrogen dioxide means reddish brown color gas. which is gas. Reddish brown color gas is nitrogen dioxide. Nitrogen dioxide gas. Only lithium nitrate will give. Whereas potassium nitrate, sodium nitrate will give their respective nitrites. This is called potassium nitrite. Potassium nitrite. So sodium, potassium, rubidium, cesium carbonates by nitrate, sorry, sodium, potassium, rubidium, cesium nitrate on heating gives their respective nitrites and oxygen gas. Whereas lithium nitrate alone gives lithium oxide, lithium dioxide. Actually, this should be lithium oxide, Li2O. This formula is wrong. Lithium oxide, this is Li2O. Please note it. Li2O. Lithium oxide along with nitrogen dioxide and oxygen gas. So please make this difference. Note this difference, very, very important. Next continuation. So let us see now diagonal relationship of lithium. Similarity with in properties with magnesium. Lithium and magnesium have almost same atomic and ionic radii. Lithium and magnesium have almost same atomic radii and ionic radii. Lithium and magnesium are hard metals and lighter than other metals in the same group. Lithium and magnesium react slowly with water. React slowly with water. Lithium and magnesium form hydroxides which are weak bases. And more important, like how magnesium also combines with nitrogen in air and forms their respective magnesium nitride Mg3N2. So 3 Mg plus N2 gives us Mg3N2. So like lithium, how it forms lithium nitride, magnesium also forms magnesium nitride. Lithium and magnesium form hydroxides which are weak bases. So the basic character increases down the group. Lithium and magnesium forms monoxides and nitrides, as I told you. Lithium and magnesium forms monoxide and nitride. So for example, magnesium when burns in oxygen, it forms magnesium oxide. 2 Mg plus O2 gives us 2 MgO. Similarly, magnesium combines with nitrogen and forms magnesium nitride. 3 Mg plus N2 gives us Mg3N2. So in both the cases, lithium also forms oxide as well as nitride. Lithium and magnesium carbonates undergo decomposition. So the carbonates, lithium and magnesium carbonates undergo decomposition on heating gives respective oxide and carbon dioxide. Very, very important. So lithium and magnesium carbonates, that is Li2CO3, on heating strongly forms lithium oxide plus carbon dioxide. Similarly, magnesium carbonate also MgCO3 on heating strongly forms magnesium oxide plus carbon dioxide. So very, very important. Both lithium chloride and magnesium chloride form hydrated salts and they are deliquescent. So both lithium chloride and the magnesium chloride are hydrated salts and they are deliquescent. So what is deliquescent? You can, I think you know it. If you don't know also, refer the book. Next continuation. Next we have compounds of sodium. So as we have completed all the general properties, general physical and chemical properties of alkali metals commonly. Next we have preparation of alkali metal compounds, that is compounds of sodium, preparation properties and uses. Sodium carbonate, washing soda, also called as washing soda, sodium carbonate. More additional points we'll discuss in the next session. Now, preparation of solvent process. This is also called as ammonia soda solvent process. What is this called? Ammonia soda solvent process. So, first step, what happens? Ammonia is combined with carbon dioxide and water. It forms ammonium carbonate. This ammonium carbonate combines with carbon dioxide and water. It forms ammonium bicarbonate. And the ammonium bicarbonate on reaction with sodium chloride, it forms ammonium chloride along with sodium bicarbonate precipitate. This downward arrow represents it is precipitate. The sodium hydrogen carbonate, that is sodium bicarbonate, is prepared and heated to get sodium carbonate. So what is the sodium bicarbonate or sodium hydrogen carbonate formed in the above reaction is heated strongly in the air and forms sodium carbonate, carbon dioxide, and water. So the ammonia is recovered by treating ammonium chloride with calcium hydroxide. So ammonium chloride when treated with calcium hydroxide forms again ammonia, calcium chloride in water. So this ammonia is again used combined with carbon dioxide in water to form ammonium carbonate. This ammonium carbonate on heating with carbon dioxide in water, it forms ammonium bicarbonate. Ammonium bicarbonate on reaction with sodium chloride forms ammonium chloride along with sodium bicarbonate. So this is called a continuous process and this is called preparation of sodium carbonate. It is also called as washing soda, common name. So washing soda by ammonia soda solvay process. Why we got it as soda? Because it forms baking soda in the intermediate steps. That is sodium bicarbonate is also called as baking soda. That's why it is called ammonia soda solvay process. This diagram is not required. Next, sodium carbonate properties. So that is the preparation of sodium carbonate. Sodium carbonate is a white crystalline solid which exists as decahydrate. Decahydrate means Na2CO3 dot 10H2O. On heating, washing soda loses the water of hydration and becomes yellow anhydrous sodium carbonate. So white changes to yellow color on heating, which is known as soda ash. When exposed to air, it forms sodium carbonate plus water. So this process is called as efflorescent. So removing water of crystallization is called as efflorescent. This is nothing but what? Removing water of crystallization. Water of crystallization is called as efflorescence. Removing water of crystallization is also called as what? Efflorescence. Sodium carbonate on heating strongly, it forms sodium carbonate along with water. So this is called efflorescence. Next continuation. Sodium carbonate is a salt of weak acid and strong base. How can we say? Because sodium carbonate, how does it form? Sodium combines with carbonic acid. So carbonic acid is weak acid. So sodium carbonate is there. So from weak acids, it forms sodium carbonate. And from strong base, sodium hydroxide is strong base. So from sodium hydroxide, you will get sodium. You get what? Sodium. So this sodium and bicarbonate combines together and forms sodium carbonate, H2CO, HCO3 actually, carbonic acid. So that's why you can say sodium carbonate is a salt of weak acid and strong base. The carbonate ion undergoes hydrolysis to give hydroxide ions. Hence, the solution of sodium carbonate is alkaline in nature. Because when sodium carbonate is dissolved in water, it forms bicarbonate ions along with OH minus. So that's why we can say this is basic in nature, alkaline, because due to the formation of OH minus ions. Due to the formation of OH minus ions, so the solution of sodium carbonate is alkaline in nature. Very important, very important point. Due to the presence of OH minus ions, the solution of sodium carbonate is alkaline in nature because when you dissolve sodium carbonate in water, it forms bicarbonate ion along with OH minus ions. OH minus ions represents basic. Represent what? Basic. That's why it is alkaline in nature. Next continuation. Use of sodium carbonate. Sodium carbonate is used in hardening of soft water. Sorry, softening of hard water. Sodium carbonate is used in softening of hard water laundry. It is used in the manufacture of glass, soap, borax, and sodium hydroxide. It is also used in paper industry, textile industry. It is used as laboratory reagent. So what is soap? Every day we use soap for bathing and even this also. What is salt commonly called as sodium salt of fatty acid? Sodium salt of fatty acid. Fatty acids are called what? They are called as soaps. Sodium salt of fatty acids are called soaps. So that's why sodium carbonate is used in the manufacture of glass, soap, borax. Borax is nothing but boiling powder, and sodium hydroxide, that is caustic soda. What is sodium hydroxide? It is also called as caustic soda. And it is used in paper industry, textile industry. It is used as laboratory reagent and it is used in softening of hard water. What is hard water? What is soft water? We'll discuss in hydrogenous compounds. And even this is laundry for dry cleaning purpose. Now, let's see. Why is lithium carbonate decomposed at lower temperature, whereas sodium carbonate decomposes higher temperature? As lithium carbonate is less stable, less stable when compared to sodium carbonate. When compared to what? Sodium carbonate. Because as we go down the group, the stability of carbonate increases. The stability of carbonates increases. That is the statement. So lithium carbonate is less stable when compared to sodium carbonate. Hence, it is decomposed at lower temperature. Hence, it is decomposed. It is decomposed at a low temperature. So when lithium carbonate is heated strongly, what does it forms? It forms lithium oxide along with carbon dioxide. Simple. Next continuation. Write balanced reactions equations for the reaction between sodium peroxide and water. Very, very important. Already we know when peroxides are dissolved in water, what happens when peroxides are dissolved in water? They form their respective oxides along with, hydroxides. Sodium hydroxide. First, it will form basically sodium hydroxide. When peroxides are dissolved in water, they form respectively sodium hydroxides along with oxygen gas. Potassium peroxide is the same. Sodium oxide and carbon dioxide. When sodium oxide, sodium monoxide combine with carbon dioxide forms sodium carbonate Na2CO3. So potassium also same reaction. You can note down. Next continuation. Why are lithium salts commonly hydrated and those of other alkaline usually anhydrous? Lithium has low lattice enthalpy. Lithium salts has low lattice enthalpy and hence these salts are easily hydrated. These salts are easily hydrated, whereas other salts have high lattice enthalpy. That's why they are not easily hydrated. That's why they are usually anhydrous because they have high lattice enthalpy or low hydration enthalpy. High lattice enthalpy or low hydration enthalpy. Low hydration enthalpy. So due to this only other alkali ions usually are anhydrous because they have high lattice enthalpy or low hydration enthalpy. Whereas lithium has low lattice enthalpy and hence these salts are easily hydrated. So please note down in your class the solution. Next question. So these are the questions we have discussed right now. Now let us start. Let us discuss some other questions in this lecture. I am sharing another slide. So some more questions we'll discuss now based on this very, very important concept. So that's why I'm using whiteboard now. So right now we'll share because this sharing of these questions will be completely given in the book. Now question number 4. Let us take question number 4. What is question number 4? Potassium ion is isoelectronic with potassium ion is isoelectronic with isoelectronic with option A, it is sodium ion. Option B, it is neon. Option C, it is argon. Option D, it is cesium plus. So what is isoelectronics which contains same number of electrons? What is this? Isoelectronic means solution. I'm giving hint here. Can you see? Isoelectronic means which contains same number of electrons. So when you remove one electron from potassium, it comes to potassium atomic number is 19. For K plus, it should be 18. 18 means it is argon. So answer is argon. So potassium ion is isoelectronic with argon. Sodium ion is isoelectronic with neon. So remember this, very, very important. Now next question number 5. Let us see now. Which of the following which of the following decomposes which of the following decomposes on heating? Which of the following decomposes on heating? Option A, it is lithium hydroxide. Option B, sodium hydroxide. Option C, potassium hydroxide. And option D, cesium hydroxide. Option D. So, which of the following decomposes on heating? Which of the following decomposes on heating? So, what is the right answer? It could be, just see here now. So, imagine this lithium hydroxide or sodium hydroxide, lithium hydroxide, sodium hydroxide, potassium hydroxide, and cesium hydroxide. What is your expectation now? So, simple it is, very easy since already we know lithium hydroxide is the answer because it has lithium hydroxide has low lattice enthalpy. Lattice enthalpy, that's what we are discussing. Since lithium hydroxide has low lattice enthalpy, it is easily decomposed. So next question now. Question number 6. Question number 6 now. A neutral sodium salt. A neutral sodium salt on heating. Neutral, they are giving sodium salt A on heating liberates a gas. Liberates a gas B, leaving a highly alkaline residue. A highly alkaline means it is soluble. Alkaline residue C. Residue C. The gas B, the gas B is colorless, odorless, is colorless, odorless, and turns lime water milky. Is the only hint they have given. Now they are asking which salt it is. A is option A, it is sodium nitrate. Option B, it is sodium bicarbonate. Option C, it is sodium carbonate. And option D, it is sodium chloride. So a neutral sodium salt on heating liberates a gas B, leaving a highly alkaline residue and leaving a highly alkaline residue C. The gas B is colorless and turns lime water milky. That is the only option we have. Lime water milky means definitely we can say carbon dioxide is the gas which turns lime water milky. So carbon dioxide is the gas which turns lime water milky. Now, from where we'll get carbon dioxide? Either from sodium bicarbonate and sodium carbonate. Because easily we can say, I'll write the hint here. Since carbon dioxide is a gas which turns lime water, that is calcium carbonate, milky due to the formation of calcium hydroxide. Lime water turns milky. So definitely the option could be either B or C. Now let us see sodium bicarbonate on hot strong heating. Sodium bicarbonate on strong heating, it forms sodium carbonate Na2CO3 plus carbon dioxide. So this sodium bicarbonate and leaving a high alkaline residue C. This is alkaline residue C. This is B and this is A. Then only it is applicable. So answer is sodium bicarbonate. Because when you heat sodium carbonate, it will not form carbon dioxide. Definitely we should get carbon dioxide because carbon dioxide is the gas which turns lime water milky, which makes lime water turn, which lime water turns milky, which makes lime water turns milky. So that's why the answer is sodium bicarbonate. So like this analytical questions you'll get from properties. Next question. Question number 7. So few questions are very important. That's why I'm discussing now. Which are the following elements? Which of the following elements? Which of the following elements combines directly with nitrogen? Directly with nitrogen. Which of the following elements combines directly with nitrogen to form its nitride? To form its nitride. So it is quite simple. We know the answer. Option A, it is lithium. Option B, it is sodium. Option C, it is potassium. Option D, it is cesium. So which compound can form easily with nitrogen? Already we know this is the answer. So lithium is the only element which can combine directly with nitrogen. Lithium combines directly with nitrogen from air and forms lithium nitride. So it is 2. So it is 6. Whereas other elements cannot form. Next question, question number 8. So like these questions you'll get in the entrance examination. So please note down. Next question. Which are the following alkali metal carbonates? Which of the following alkali metal carbonates? Alkali metal carbonates. So the following alkali metal carbonates decompose easily by heating. Decomposes easily by heating. Option A, it is lithium carbonate. Option B, it is sodium carbonate. Option C, it is potassium carbonate. And option D, it is cesium carbonate. So which is the right answer? Easily you can expect. Because of low hydration, low lattice enthalpy, lithium carbonate can be easily decomposed because of low stability. Because the stability of carbonates increases, the stability of carbonates increases down the group down the group of alkali metals. So you please note down this explanation also in your classwork. So this is the answer. The stability of alkali metals, carbonates increases down the group of alkali metals. Next question. Next question is question number 9. Question number 9. Let us start now. So many questions we have to discuss, but only important models I am taking because next, the paramagnetic species is the paramagnetic species is option A, it is lithium oxide. Option B, it is potassium peroxide. Option C, it is sodium peroxide, it is potassium superoxide. And option D, it is cesium oxide. So the paramagnetic species among the following is, as already we know, all peroxides are paramagnetic in nature. So all superoxides. So potassium superoxide, potassium superoxide is paramagnetic in nature. Potassium superoxide is paramagnetic in nature. And if you see the structure of potassium superoxide, I will draw the structure here. Please note it down in your classwork. So potassium superoxide is paramagnetic in nature. And if you see the structure of potassium superoxide, let's show you the structure of superoxide. Please note down. So just writing it now. Please note it down. In superoxide, the oxygen state of oxygen is -1/2. This already we know. So you see the structure of superoxide. Okay. In the next session, we'll discuss that. So potassium superoxide is paramagnetic in nature because the oxidation state of oxygen in superoxides is -1/2. Oxygen is -1/2. Very, very important point. Next question. Question number 10. Question number 10 now. Yes, this is previous JEE mains question. Very, very important. The metallic luster. This question is important. Please note it down. The metallic luster. The metallic luster exhibited by sodium. Exhibited by sodium. The metallic luster exhibited by sodium is explained by option A, diffusion of sodium ions. diffusion of sodium ions. Option B, oscillation of loose electron. Oscillation of loose electron. Option C, excitation of free protons. Excitation of free protons. And option D, it is nothing but existence of BCC, existence of body-centered cubic lattice, existence of body-centered cubic lattice, body-centered cubic lattice. This question is very, very important. This has come for JEE means. So, then what is the question now? The metallic luster exhibited by sodium ions. The metallic luster exhibited by sodium ions. The metallic luster exhibited by sodium ions is sodium is explained by sodium is explained by option first option, diffusion of sodium ions, oscillation of loose electron, excitation of free protons, existence of body-centered cubic lattice. So answer is oscillation of loose electron, because the sodium metal is having one free electron, that is called as loose electron. So answer is excitation of loose electron. Due to the oscillation of loose electron, due to the oscillation of loose electron, the metallic luster is exhibited by sodium. Very, very important question. Next question. So this is question number 10. Next we'll discuss question number 11. Question number 11 now. A solution of sodium metal. A solution of sodium metal. A solution of sodium metal in liquid ammonia. A solution of sodium metal in liquid ammonia is strongly reducing due to the presence of strongly reducing due to the presence of. This question is also very important. Option A, sodium atoms. Next, option B, sodium hydride. Next, option C, it is sodium amide. Already we know when sodium dissolved in ammonia it forms sodium amide. But option D, it is solvated electrons. Solvated ammoniated electrons, that is solvated electrons. So, the solution of sodium metal in liquid ammonia is strongly reducing due to the presence of solvated electrons only. Answer is what? Solvated electrons. Very, very important. They will form ENH3 taken twice. This is nothing but solvated electrons. Next question. Question number 12. Next question. So this is the last question we are discussing now from this session. Potassium gives a dash color to the Bunsen flame. Potassium gives a dash color to the Bunsen flame. So what color it will give? Option A, it is violet. This is nothing but flame test of alkali metals. which are discussed in lecture 1. Next is blue. Next is apple green, and fourth is brick. So what is the answer? Potassium gives. So we know flame colors of lithium, sodium, potassium, rubidium, and cesium. So all will give response to flame test. So now the answer for this question is it is nothing but violet color because potassium will go violet in color. So answer is violet. So with this, I am ending this session. In the next session, we'll discuss some more topics based on these S block elements. So far, we are done. Some questions based on H block elements and preparation of sodium carbonate from ammonia and soda solvent process. In the next session, we will come up with a new topic. So please follow what we discussed in the class. Thank you all.